Thank you for tuning into This Automation Life, brought to you by Brenner-Fiedler. I'm your host, Paul Oppenheim, and each week we discuss technologies used in automation. And this week, Jeremy Schubert, our automation guru specialist with Brenner-Fiedler, is here to discuss measurement topics. Jeremy, thank you for being here with us today.
Thank you for having me, Paul.
Excellent. So, Jeremy, measurement, how does that apply to the automation world? And where do we even go with this?
Well, there's it's mostly applied in equipment that would be like a transducer or a measurement of some type. Like you could be flow meter, a temperature probe. It could be a pressure transducer. It's also applied a lot in motion. So that's kind of the areas. Basically, anywhere where you've got to interface the real world to the machine world. You need to know what you're measuring and.
Gotcha. So it's not enough to simply have a discrete on-off. I'm there. I'm not there. I've reached my destination or not. It's how much and how far have I gone, and just having that feedback is.
You got it. Yeah, we're getting into the analog signals and the analog of reality.
Gotcha. Okay, great. So then I guess when it comes to these measurement topics, if I kind of know, let's say if we're talking about either temperature or whatever it is, there must be certain things I need to be keeping in mind of knowing which one I should be purchasing. And so what are some topics I should probably keep in the back of my mind when I go and pursue one of these?
Well, so we're going to focus on a few things. There's kind of four, I think, interrelated vocab words, I guess, that everybody uses and that you need to know. And it's accuracy, repeatability, linearity, and resolution.
Okay.
So those are the four, and they all have some play basically in knowing what you've got to use, and you also got to know what you're trying to do. So, I guess I'll start with accuracy, unless you have any preference.
Yeah. No, I don't. What exactly is accuracy, Jeremy?
Okay, so the typical way that I see accuracy and repeatability explained, because it's often mistaken because they're kind of difficult to get a good understanding of and grasp of it, is. Accuracy, I always see this dartboard representation. So if you think of accuracy, accuracy is basically how close to your target do you make it. So in the context of a dartboard, if you're aiming at the bullseye, then it's how close can you get to that bullseye is how accurate you are.
Okay, gotcha.
So
makes sense.
That if you picture darts that are all somewhat grouped near the bullseye, but may or may not be hitting the bullseye, going around into maybe a circle of the bullseye. Those are pretty accurate, right?
Yes.
I mean, you're not way off the edge of the dartboard. You didn't get it stuck in the wall like I would. You're close. You're accurate. Right. But then there's repeatability. So repeatability doesn't necessarily mean that you hit your target, but that you were basically wrong the same way every time.
Okay.
So if you think of repeatability, you'd look at a dartboard and you'd say every dart is grouped really close together, the more repeatable you are. But that doesn't necessarily mean they're grouped together on the bullseye.
Okay.
They may be grouped together on the 19 or the 3. They may all be off on the wall, but they're in the same spot of the wall.
Okay, maybe this might seem like an odd question, but is there ever an advantage to have something that's repeatable over accurate? Or do you always... Is accuracy ever an advantage over the other?
So that's the weird thing.
Okay,
so
all right.
It all goes to, I guess, back to how repeatable are you versus how accurate are you, and then actually what it is that you're trying to do.
Okay.
I'm going to come up with an example while I'm talking, but
all right.
The repeatability, you could be more repeatable than you are accurate.
Okay.
So that might be tough.
Yeah.
But it could be that every time, let's say we're measuring temperature.
All right.
And let's say every time you're trying to measure 80 degrees Fahrenheit, because that's a temperature I think everybody can imagine.
Okay.
It's actually 80. Let's say this perfect world of 80 degrees out. I don't know if that's a perfect temperature, but it's 80. We're going to agree to that. The temperature probe could say that it's 79, and it could say that it's 81. And so at that point, we'd say, okay, you're accurate to within a degree.
Right.
You could also take a look at it and say, okay, every time that we measure, we're always off a degree, but it's 79, 79, 79, 79.
Right.
So that's repeatable, like to 0.0, which isn't very realistic. But
okay.
So now you're repeatable to 79, let's say it drops to 75 is the real temperature outside. And again, you're measuring 74, 74, 74. So your accuracy is still 1 degree, but your repeatability is better.
Right.
It's better than 1 degree. So what you can do with that number is, okay, my accuracy is off by 1. I'm always repeatably off by 1.
Right.
So you can build that into your system. And
Okay.
you can say, I'm going to basically linearize my overall system because it's repeatable. It's just not that accurate.
Okay, so you'd program with some sort of an offset or something like that.
Yeah, an offset or like a lookup table or something.
Right.
It's just, I can repeatedly go, when I go to 70 now, maybe I'm off by 2 degrees. But every time I go down to 60 and back up to 70, or up to 80 and back down to 70, I'm always off by 2 degrees.
I see.
So now you do lookup tables a way to do it. You make maybe a linearization algorithm or something to compensate for it. There's kind of a couple ways you can do it, but that's when having good repeatability can actually make you more accurate as an overall system, even though your sensor may be less accurate.
Right, so obviously accuracy plus repeatability, you want both to be good. Obviously you want to be striving for that, but there's too many other factors, I'm sure, external, being like maybe temperature or other things that could be affecting your instrument, and so they give you these specs to kind of like cover themselves a little bit, so to speak. Forgive the sensor, so to speak, because of these other environments
that's always possible.
Okay.
Yeah, I mean, depending on the type of sensor. So, it's like the electronics that are built into there. Maybe there's some kind of element that's sensitive to external, like ambient temperature.
Or just thermal expansion of the components when you first power it up. Maybe as it warms up, or whatever the case is, maybe that will affect it a bit too. Okay.
Yeah, that's all possible out in the measurement equipment world. So you got to wait for everything to kind of normalize.
Form a little equilibrium.
And that's true of some equipment, but not always the case. So
Okay.
it's a case by case basis on the equipment. So I hope that everybody doesn't take that as you always got to wait for things to warm up.
Right.
And that was more, I think, a factor. The older electronic equipment is, the more that was an issue.
Right.
And now things I think are a little more stable.
They've improved the technology, so they don't have to have those disclaimers in the book.
I won't go into why, and I'm not sure that I'd explain that well, so I'll stay away from that.
Okay.
So
you mentioned a couple other topics, I think, as well. Things to lift up, and what were those?
So linearity is one, and this is when you talk about accuracy, you're usually talking about how accurate am I measure something. Mm-hmm. Linearity is usually the spec that you use to determine your accuracy.
Okay.
So it's a lot of times given as a percentage, maybe like 1% of full scale.
Okay.
Is like a typical specification you'd see, and what that is if your full scale is 100 degrees Fahrenheit and your linearity is 1%, it's saying that you're going to be basically 1% of 100 degrees off. So you're going to be 1 degree off across that range.
Anywhere from 0 to 100, anywhere within that you can expect to be off.
And sometimes it's plus and minus, so you got to really watch that. Is it plus and minus 1 degree, or is it 1 degree? Because that's a quick way to actually double your error, your measurement error from accuracy. Actually, while I'm on the topic, I forgot to bring up the error typically is your accuracy plus your repeatability.
Right.
So if you've got a repeatability spec of 1 degree and an accuracy spec of 5 degrees, and your error is 6 degrees.
Okay.
You can't really, you may be able to get the equipment to do better than that, but you can't really ask for more than that.
Right.
Or you're not guaranteed it, that's for sure.
Gotcha.
So the linearity, does that make sense? Linearity is kind of like, is the, I guess, general way to calculate and find your accuracy.
Right, so I'm thinking, like, how's your accuracy and repeatability, if we're talking about temperature, let's say, what's the accuracy and repeatability at 0 degrees Fahrenheit versus your accuracy and repeatability at 100 degrees Fahrenheit, and does that at all change as you're going up and down the scale of it, or is that even another topic?
The short answer is yes. So that's what you get to. It's 1% of full scale, so this is where, everybody's always wanted to try to push it a little further. So if I reduce my scale, then I don't need 100 degrees. I'm looking at a 10-degree window.
Right.
So I got 1% of 10 degrees. Mm-hmm. Do I have 0.1 degree accuracy? And no is the answer.
Okay.
Maybe is also the answer.
Right.
So it's when they give that linearity spec, the manufacturer of some equipment has measured it over the span.
Right.
But they're not guaranteeing that it could all happen in one place. It could all happen spread out throughout the full scale.
So would that mean that you could get a better accuracy spec, if you will, if you reduce that overall full scale? So instead of going 0 to 100, I'd say, hey, I'm only be using between 40 and 50 degrees. So,
The short answer is no, but you probably would see something a little better.
okay.
No one is ever going to give you a guarantee, but that scale is probably spread out over the full thing as opposed to all the air being pushed into one small section of the full scale. So
Absolutely, and I would imagine
official
that,
answer, no.
right.
Yeah.
But that's why the factory is going to give you probably the worst case scenario.
Yes.
Because in even each instrument that they send out with all of those electronic components, even those components must have different things that will affect it. So every instrument, even though they make the same thing, each one's going to have a tiny quirk, if you bet, I imagine, with each one. So they're going to give you, here's the worst case scenario you're going to have as far as accuracy, repeatability, linearity.
Always plan for the worst. But, you know, and then their worst case scenario, though, is always in a controlled lab environment using these exact materials and whatever. So their worst case scenario is your best case scenario, but then you reduce this, it gets a little complicated, and usually it just ends up being, let's test it.
And I'm sure they cover themselves with extremely conservative specs so that you can relax, so to speak. Okay, and you mentioned there was another topic you wanted to mention.
Resolution.
Oh, that's it.
Yeah.
Okay.
So resolution gets tricky, especially in motion, because people always look at, hey, I've got this encoder and it's 6,000 counts or 3,000 counts per revolution, and I got that connected to a lead screw that's this many inches per resolution. So this is my accuracy, right?
Right.
And no, definitely not.
Okay.
That's your resolution. That's how small of an amount of a change you can see.
Yes.
Whether or not that change is real, or if it's accurate, or if it's repeatable, it really doesn't do anything.
Okay.
It's nice to have the resolution for control, but sometimes that extra resolution could throw a control loop, for a little bit of a loop.
Would that also be considered like the displayed resolution? So let's say we're looking at temperature, and it's displaying to 1/10 of a degree. Would we say that if something is even less than 1/10 of a degree, it's either going to be rounded up or rounded down, so to speak, to that particular 1/10 of a degree, because that is its resolution?
Yeah.
Anything in between, it just got to go click one way or the other.
Right.
Okay,
Yeah. That's so.
Okay.
The resolution of maybe a temperature probe may be very, very small, but then if your display resolution is only 1/10, then you've got realistically more resolution that you're just truncating or rounding.
Right.
Yeah.
Sure.
So that's kind of the two, and I think a lot of times people look at the resolution they have of a system and say, yeah, but I can measure it to 0.01. Well, no, you can see changes that are 0.01, but those may not actually be the real changes.
Sure, absolutely.
So that number, it's tough to say the number becomes worthless, but it kind of does.
Right.
So,
Okay.
Yeah. And that's, I guess those are the four topics.
Okay.
But I know other than that, I think that with measurement, it always gets into this, you've got to test it. And the more important thing is, what do you really need to do? Like, you can get as probably accurate of equipment as you need, but the more accurate it needs to be, it's usually more expensive. So what do you need to do? Start from there and just hit what you need, and that's it.
Gotcha. Okay, very good.
Cool.
So at this point, it looks like we tackled some of the most important measuring topics. So Jeremy, thank you. So again, that's all the time we have this week. Thank you, Jeremy, again for joining us, and thanks to all of you for listening to Brenner-Fiedler's This Automation Life. If you have any questions about what you've just heard, or if you have a topic that you would like to hear discussed, please email us at tech@brfa.com. That's tech, TECH, at brfa.com. And be sure to continue tuning in each week. We have some more fascinating episodes coming up, so stay tuned.